Oui. Thank you. So welcome to Stefan Schoder, who is an assistant professor at the University, Technical University of Graz. So your talk is about some insight of this active teams in Graz. So I let you. Thank you.
Yeah, thank you for the kind introduction and for the opportunity you gave me to stay with your group. For a warm welcome. And should I take the mask off?
Yes.
It's probably more convenient for me and for you. So the talk will be introducing a little bit about what we're doing at the TU Graz. It's now the 1-year anniversary of Graz from the TU. Built up their small acoustics group, about 3 PhD students and 4 working students. And then I will give some insights on the theory of Helmholtz decomposition as I did in my PhD, and which brought me here. Okay, then start with the research. So just short recap. Etienne was already announcing here from about 3 months here from. And we are jointly developing something related to Helmholtz decomposition, and I will at the end of the talk give some insights how I obtained this graphs and what's the theory behind it, why we use finite elements. So first I'm talking about the research we are doing at the TU Graz and what I'm especially doing at the TU Graz related to the acoustics group. The tradition of the Technical University of Graz is that we have about 50 years this audio engineering studies. They are quite well known in Austria and the Lower German region. Very attracted by the automotive industry, established products regarding acoustics. And this is very deeply connected to the electrical engineering department, and that's why I'm also there. I do teaching about 40% of my weekly thing. Acoustics, we're now developing a computational acoustics lecture, and we are studying a lot and teaching the multi-physics simulation using finite elements. This is also quite deeply related to our software we are using. We are developing the software OpenCFS. It's an open source project. I think also about half a year ago it was launched as an open source project, but it's continuously developed by our group about 15 years. So it's quite strong and robust multi-physical simulation code. The commercial pendant would be console. It's under the MIT license, so if anyone of your group like to adopt it and use it for a commercial project or anything else, you can just go for it and use it. Also without any license, and you can use it for every purpose you would like to. There's no limitation. There's also commercial support available and stuff like that. Anyway, we can have a look at the website at the end of the presentation. And I'm doing research with my group. We have now 3 PhD students doing some different projects about human voice, some fan voice applications, turbocharger compressor simulations, and some piping systems for electrical vehicle stuff and cooling. And for working students, just a link to some research, some latest publications we did, if you're interested. Good. Very interesting project we are quite confident on and quite known for last year's in the Human Voice project. We are jointly developing with the model Sing Voice with the University of Erlangen, and they are the medical department. They are doing a lot of measurements from people, like the vocal fold motion, how it works, and also the influence of different parases or cancer-like structures on the vocal folds. And we are then trying doing the whole simulation chain to develop an acoustic workflow to actively predict how clinical injuries are repaired and how they will be affected in the final voice. This is more or less the goal of the project. We are now in the half time, and we are now waiting for the second period to be funded. And we are in the second period. We are looking at typical cancer structures on the vocal folds. So yeah, that's the Sing Voice project. But I will not talk about the Sing Voice project in the scientific part of the talk. I will talk about the Helmholtz decomposition, how we separated longitudinal structures from vertical structures in the flow field. And therefore, I separated my talk into three subsections. First, we will talk a little bit about the physics of the equations, what we are dealing with, and how the physics of the equations is related to the solution strategy we are using, and using finite element, the basis functions regarding the finite element method. And then I will show the application of the cavity you saw before in the teaser, or also at the end of this presentation. Okay. Yeah, then starting with the physics. The idea is that you can separate vertical structures from some compressible structures, longitudinal structures, and yeah, there is some kind of theory or vortex sound developed by Paul, and this was more or less the starting point of why we started to be interested in separating vertical structures from some processes. And then there's also a very interesting connection, how 1980 defined the acoustic potential regarding a Helmholtz decomposition and said, okay, this will be the acoustic potential. We were aiming for defining not the acoustic potential, but the compressible potential, which in the limit to the far field will converge to an acoustic potential, and also is more or less defined in the near field, so where vertical structures are. Yeah, interesting. This is a Helmholtz decomposition, so it's the velocity field. And here we have some longitudinal process and some vertical processes, and yeah, directly seeks for applying the Helmholtz decomposition and getting some post-processing out of it. Okay, here we have some longitudinal processes, as I said, and these longitudinal processes look like this shape, and they are associated with the compressibility of the fluid field. The vertical processes look more or less like this, and are associated with some vorticity, which is in the fluid. And yeah, so this would be the acoustic potential defined by how. And the question now is, how did I take 1, 2, 3 fields? And the question for me at starting at the PhD was, what's this guy here? So we have kind of a field by null, and this field is simply looks like this, and it's more or less a stagnation point of the fluid, which is the homogeneous solution of any Helmholtz decomposition variant. It describes a stagnation point, which ensures that the divergence of the velocity field is zero and also the curl of the velocity field is zero. And it's simply trimmed by when you do a fluid cutout, either it's more or less ensured by the boundary conditions. So you're more or less having this due to the boundaries, or if you have interior cutouts, like having just the body inside your fluid domain, then you will expect stagnation point. And this is why this third component is in here. Okay. The three components already were described quite nicely in the book of Batchelor, 1967, and referring it like an easy task. If you are in a free field configuration, you can simply say that the decomposition is unique and you have this scalar potential and this vector potential, and this will work. You apply the Green's function, everything is more or less very well defined, so well posed system of equation, and all went smoothly. Easy, yeah, usually it's not that easy, but yeah, you simply can do it. So we said, okay, this is kind of a compressible shape. The vector field is the vertical field. And now the challenge comes when you have boundaries and interior cutouts, like bodies in the domain, you get this potential flow part. Yeah, the question is, when you do now the Helmholtz decomposition, where will it be? Will it be in this potential, in the joint potential, or in this joint potential? We did it in the AAA Sherlock propagation, that it can be either inside there as the homogeneous solution of the PDE, or inside this potential. We showed it there. And defining your boundary conditions will then say where this is more or less entering into the decomposition. Yeah. In the introduction, as talked about, that we use finite elements. Finite elements usually are based on typical function spaces, like the H1 function space, simply Lagrangian nodal finite elements, or H curl, like H elements, or also called Nedelec elements. And these different function spaces fit quite well to the decomposition. And these function spaces are also related to each other by the run sequence of Sobolev spaces. Then when we have an H gradient space, then we can go to the other Sobolev spaces by simply the sequence. And the sequence also tells about the interpolation properties you have in finite elements, and how to go from a continuous space to a discrete space. And in the discrete space, if you are in this DRAM homology, then it's also in the discrete space fulfilled. It's a quite nice property. And relating to the Helmholtz decomposition, the H gradient, usually this Sobolev space is used to model this functions, the gradient field, and the H curl is used for modeling this one, because it already has this curling property in there. It doesn't need so a strong resolution to get the vertical structures. So getting on with the sluice strategy, we already were talking about the function spaces. I will go back just once into the theory. I already described the theory of vortics, how to the easy case with the Green's function. I think it was very novel and proper to this time. but now we have a lot of computational resources available. Time changed a little bit. But the interesting thing was that Paul was already aware of that we have this potential flow part, but he in the setup, having the free field setup, he didn't worry about it because it was simply not the point to make there. The thing is now we are using finite element to model and tailor to its functions, so also to incorporate boundaries and interior cutouts. And yeah, therefore we use the finite element method to solve the problem. So having a bounded finite element domain, or a simply bounded simulation domain, we're having this Helmholtz decomposition up there. We already spoke about it, that we're using the H-curl representation for modeling the vector potential, and we will see in a minute why this is beneficial and how this is connected to the vertical structures. So the idea is to have a bounded domain. We simply take the curl of this equation there, and we end up with this PDE. And for this PDE, we now like to find a solution, and yeah, regarding the boundaries should comply with the fluid solution we already obtained. The thing is, the right-hand side is fully determined by any flow simulation, which should be accurate enough and conversion that really the U is modeled, and everything, the whole knowledge of the decomposition is always placed in this U. So all vertical structures, compressibility is simply in the U, and this is just a linear post-processing of the velocity. Just for having the opportunity to apply finite elements, we have to derive the beach formulation. Just integrating over the domain for applying test function to it, then doing integration by parts. We get the boundary term, which is an inhomogeneous Neumann boundary. We have to apply it, and then we prove that if we do regularization in the finite element context, it's also shown in the AAA shown Propagation, that this really solves the problem of decomposition regarding the set of boundary conditions. And we are using the OpenCFS solver to solve it. Yeah, spoke about before about the H-curl. We're going back to the H-curl. So the H-curl accounts for the vertical shape functions. So it means these are H-curl shape functions. They already, based on a node, they already are curling the field. So these shape functions are deeply related to this vertical structures. And therefore, we don't need so many elements to represent the verticity. And furthermore, if we use this function space, we can also show that we have this best approximation property of finite elements, that indeed it converges to the true solution of the physical problem we have in hand. And yeah, that's simply how to do it. If one uses here a different function space, it will also converge. It needs much more elements, but it's not proved by a math that it will converge to the true solution. But anyway, we will have some error, which is very small. Yeah, then we're going to the application. In my PhD thesis, I did some applications to a cavity simulation, which was carried out by Thomas Kuhn and the team of Munz in Stuttgart. They were using to obtain these fields, they are DG solver flexi. And yeah, see here that we have some vertical structures in the vicinity of the cavity and some propagation of compressible structures, which be acoustics. Yeah, based on the vorticity, we now solving our problem at hand, and we are going to obtain the solution of the vertical field. So we're solving simply an elliptical PE. The PE is this one, forced by the vorticity inside the domain. We are then applying some boundaries, a homogeneous Neumann boundary. On these three sides, we applying inhomogeneous Neumann boundary, a tangential component of the velocity field. Yeah, and I will show then some plots in the volume, and along these two evaluation lines, get some interesting insight about what's going on. So yeah, we already had it. That this was the compressible fluid field decomposed in the vertical part. You don't see this radiating compressible structures in the vertical part anymore. And in the compressible part, we see these structures. Yeah, looks first sight quite interesting, but in the I-born norm, that doesn't say a lot. We then have some lots of evaluation lines. During submitting the publications, we were faced with some questions. The first question was, why is the decomposition possible to more or less say, okay, we have here some nonlinear process going on. We are applying a linear equation, and then we obtain some nonlinear features. Yeah, this is simply possible because the right-hand side already knows what's going on, and this is more or less the knowledge of the equation that the right-hand side knows what's going on. It's simply a linear post-process. Yeah, the second question is quite deeply related to the first one. Why the solution can look nonlinear? Yeah, of course, if the right-hand side looks already or has some nonlinear processing, can simply with the Helmholtz decomposition regenerate the separate field. So this is also simply because of the right-hand side. And there's also a question, can we speak of the compressible potential of acoustics? Yeah, probably in the far field, but we didn't validate it on that. So this is more or less an open question. Looking at the two evaluation lines. So here, just a reminder, the evaluation line 1 is starting at the lower corner here to get some insight also what's happening inside the cavity, and is in the direction of the main lobe of the compressible structures here. We see here the blue solid line, which is going here and starting to be wavy there, is simply the simulation of the fluid, so the nonlinear simulation of the conservation equations by a flexi solver, and then the first result, the dashed dotted line is the vertical structures, which is quite nicely following the direct simulation, having some deviations, and you see more or less in the far field of where the compressible structures are, we have really nothing. Simply compressibility is oscillating, and the vertical structure simply stays fixed position. We also see it here in the dashed lines that we have here the subtraction from these two lines here. That here we can obtain the compressible structures. And if we do the composition by the Poisson problem, so the scalar values problem, directly tracking the compressible part, we obtain this straight solution here. And as we see in the far field, we are quite close to each other. But in the near field, where vertical structures are also present, we have some deviations deviations are, yeah, we are not 100% sure about it right now. But actually, here, when we're doing simply the calculation of the compressible part, we have here a re-entrant corner, and here we have some singularity in the problem, which may, yeah, produce some errors there. But yeah, this is simply some deviation, and therefore, because we have this this singularity at this point here, we did the second evaluation line, the line 2, and there we see overall a very similar picture. But actually, we are looking at this point where the singularity actually occurs, and there we see that if we compute the compressible part by first solving the vortical, the curl-curl problem, like the A for the A, we see that the curve goes more or less then again to usually 0. Then it stays bounded. So if we solve for a curl-curl problem for a vortical structure, it stays bounded. And if we directly solve for the compressible part, we get here some singularity. Yeah, and probably imagine that it will go down. And this is also a very known issue for having a Laplace, or solving a Laplace problem in this domain. Yeah. Based on these results, I tried some propagation simulation using this convective wave equation. Apparently, it did not work. We were inserting here some, yeah, simply the, yeah, that's one here. Simply the vertical forcing, and in fact, it didn't work. Yeah. This time should not be here. Just a misprint in the slide. Yeah, apparently it didn't work. Kind of filtering the sources based just on the primary quantities like the velocity field. It didn't work. Yeah, and that's now our turn with ATM. We would like to filter the whole source to, and the idea is that the compressive part of this source is the source, the real source, and the vertical structures being inside the source will not propagate. So that's more or less the hypothesis we are now facing, and yeah, hopefully this will give us some answer that we can do it, or we can simply not do it, and closes some book about how to filter sources in, yeah, for the future. That's not kind of staying trapped in the misleading direction. So yeah, that's wasn't that just give some summary about things we already did. We solved some challenges about bounded domains and the Helmholtz decomposition. And, yeah, these 2 publications. Yeah, you will get the slides anyway afterwards. We were also quite confident about how treating the non-convex domains like the re-entrant corners, what type of equations we have to use. And we also did a radiation condition for the radiation condition for LMFA. There is the radiation condition is more an asymptotic condition. Yeah, so simply how solve the free field open, and yeah, partly solved is that we have some inconvenient solution for a boundary problem, how to separate compressible and vertical structures at the boundary. Yeah, and we are now designing a more accurate approach. We would like to do also the separation along the boundary, which is not so trivial. Yeah, would like to look a little bit into detail about the sound power integral, which was introduced by Hall. And yeah, we're now doing investigations regarding the topics very few. Yeah, thank you.
Question, comments?
The question is a teaching approach
yeah, the Thomas Kuhn in Stuttgart used the DG solver to obtain the velocity field. Yeah, but we didn't use it. So it was, they provided data. We based on the R2, we developed some interfaces to our software, and yeah, that was basically it. So we computed all the quantities like the vorticity and the dilatation using the RTG solver, and then transformed the whole data to our finite elements.
Maybe you can go on your website showing also the open source code, maybe.
Yeah. Yeah. This is the website. It's opencfs.org. Yeah, it says something about the solver itself, and yeah, we usually the solver is capable of solving different acoustic wave propagation equations, electrostatics, mechanics, magnetics, piezoelectric field, and the thermal field. It can couple magnetics with mechanics, vibroacoustics, piezo and acoustics, magnetomechanic and acoustics, and thermomechanics. Yeah. We have static analysis, transient analysis, harmonic analysis, multi-harmonic analysis, and high frequency analysis. Methods used. We have some non-conforming interfaces to account for rotating structures or simply do flexible meshing. We have model water reduction in there and some structural optimization. Anyone wants to know more about the finite element software, just tell me, or we can arrange some discussion or presentation about it. If someone is specifically interested in some parts.
Is the mechanics solid mechanics? Or
it's solid mechanics. There's no structural mechanics. We tried quite a lot in the last years to get some funding for the structural mechanics, but actually it's not a research topic, it's just an implementation topic. So we are not very happy about simply having solid mechanics, because it's used for thin structures like plates, just a lot of elements. It's not very efficient. So that's one of the main drawbacks using vibroacoustics in our solver. Then you have to model the volume. Yes, if we can go to some pictures, but meaningless anyway in this context.
Your cavity flow, was the Mach number there?
Mach 0.8. It was already quite high. Yeah, we're probably curious about if we would also manage to go or decompose it for a Mach number above 1, but apparently we didn't have any data. So, and we're not so confident that computing a validated CFD for a Mach above 1. So we didn't have any experience so far. It was a little bit too bold to just say, yeah, we can do it.
For the applications you were doing, you were talking about Batchelor. Just say what kind of study.
Yeah, it's a low pressure axle fan. Yes, very similar to this one. It's low pressure axle fan. We have the benchmark case, and it's also kind of simply a fan in a very short duct. And we did some simulation that did some proof of concept that our solver works in this concept context. This not very in the physical details about the flow, where the noises are, where the noise is generated, where the sources are located. It's more an showcase.
Because it's a very low Mach number axial flow. And the thing is that you are already using an acoustic analogy in your team based on the acoustic potential.
Yeah.
It's relying on expansion about incompressible flow. So you have only acoustic flow solution. And the point also is to validate such an acoustic analogy based not on the incompressible flow solution, but with compressible flow solution as a term to see if this is valid for mid to high Mach number.
Also, there we're usually applying this equation, which is PCWE. For this low Mach number applications and without any feedback, it works quite well. And it's also quite beneficial because in the setup, having the acoustic potential defined, you can also quite easily couple it to the mechanics and treat the feeds there. So this is also quite beneficial why we use it in the human phonation project, because there we can simply, by introducing a inhomogeneous Neumann boundary, account for the vibrations of the vocal folds. Just saying that the vocal folds are moving, and simply have the motion folds.
So the thing is note that you uncompressible unstable.
Yeah, it's an incompressible flow. It's and solved with the with the LES-like model in star CCMs. We are usually
terms this analogy of parasites. Compressible flow, you need to have the wind function of the laser. Or you compact or
the structures in there are compact. It's very so far as we determined, they're not very in the limits we that was by maximum 5 kilohertz, and it was quite compact around the tips of the template. So it worked quite nicely.
So, thank you very much.
Yeah, thank you very much.